So, first we need to know what are the properties, what are the properties of magnetism. First, I have a question to you. What do you mean by magnet, basically? Most of the people supposed to know this. What do you mean by magnet? Magnet is a substance which attracts which attracts materials or some substances. Okay, attraction is fine. Attraction is fine, and it also have directive property. It also have directive property. If anything is said to be a magnet, if anything is said to be a magnet, if it is hangs, if it is hang like this, okay, to any roof, or if you're holding, always it comes to the rest, it comes to the rest in the north south direction only, in the north south direction only, though you are tilting, you twisted, again it comes to the rest in this direction, and at the same time it attracts the materials, okay, magnetic materials, and always it shows the direction in the direction of north south only. So this is, we say it is as magnet. Okay, it should have attraction as well as directive property. Such type of materials only called as magnet. Sir, only attraction. Of course, if you take the charge particle or any charged body, that is also having attraction property. Always it is having attractive only. Doesn't have directive. But coming to here, it is having directive as well as attractive. Such type of substances only called as magnets. Okay. Now, the phenomena of attracting magnetic substances like iron, nickel, cobalt, etc. Because why these materials means these are only the magnetic material. You might know this. We studied our old earlier classes, old levels. Long, long ago, how this magnet has found, from where it has come. There was a story. A shepherd is going across the forest. Suddenly, he got, or his nail stick is attracted towards a stone. Then he found that the stone is having different powers. Then the stone was at a place is Magnesia, which is located in Asia continent. Therefore, the stone is later on named as magnesia since it is found in the area. So it is called as magnet. And since it is attracted by this iron nail in the sense, so it is having different powers. They understood, they started researching on that. And earlier it is called as lodestone. Earlier it is also called as lodestone. And after that lodestone, we also form that is also called as in a form of scientific name. It is called as magnetite. What is that? Magnetite, the name of scientific name of magnet. Fe3O4, we say it is its scientific name. Fe3O4, we will say this. Right. So that is, we call it as magnet and the magnet story, which we know. Then you can see here the magnet is having the, if you take the bar magnet, with respect to bar magnet, obviously magnet is having a polarity property. It concentrates all its magnetic properties at its poles. We found till now there are the two natural magnets. One is lodestone, which we call is a natural magnet, and the other natural magnet is Earth. Earth is a huge natural magnet, which is having the north and south poles, geographic poles as well as magnetic poles also available. There, the some amount of magnetic properties or magnetic radiation is exhibited. We know that. The region around its which exerts force on other magnets or on other objects we call magnetic field. Okay, we call it as magnetic field. What is a magnetic field? A magnet which is experiencing around its area or field is called as magnetic field. Let us say, I'll tell you here, if this is a magnet, if you place anything material around this area, automatically it gets attracted or it exerts force. Why it has attracted? Since it exerts force, then it has attracted. But beyond this region, it, here it may not exert its force. Why it is so? The field has spreaded or the strength of this magnet is spreaded over this region only, not beyond this. Okay, so this is called as magnetic field. The region or place around the magnet which is experienced by that magnet is called as magnetic field of that particular magnet. Properties of bar magnet. What are the properties of bar magnet? Bar magnet is in the shape of rectangle. Always bar magnet is having north south poles. Okay, and at the same time bar magnets, since it is having north south poles, it always attracts. North pole is towards the south pole and south pole towards the north pole. Okay, and magnetic poles always exist in a form of pairs. In the form of pairs. Magnetic field, magnetic poles never exist individual. For example, if you break a magnet, if you break a magnet like this, before it was north south, it will be divided into this is north, this is south. Okay. Again, this become north, this is become south. Again, if you cut it, again it will be spreaded into the like north south and north south. It will be further like that. How many pieces if you do, that many poles will be divided. Otherwise, it will never exist, ever exist in a form of poles. Now, a magnet can induce magnetism in other magnetic substances. A magnet can induce magnetism in other magnetic substances. It attracts magnetic substances. A magnet can induce magnetism in other magnetic substances, obviously. Like iron nail, if you're keeping iron nail, here it is attracted. One more iron nail, it's not attracting directly to this magnet, it is attracting here. So then what happened in the second magnet also, this magnet, in second material also, the magnet is inducing the field. So this property is called magnetic induction, we say, since it is without touching, inducing the field. Okay, it attracts the magnetic substances that we know. Repulsion. Always, if any place the magnetic properties are available, you need to check in the sense we will use a surety test that is called repulsion. A magnet attracts iron rod as well as opposite pole of other magnets. So, therefore, it is not sure test of magnetization. For example, at this particular area I wanted to find, so I got another magnet. Then if I'm experiencing some repulsion force, then I'll understand here some magnetism properties are available or magnetic materials are existing, magnetic substances are existing, I can tell. But if you are taking the same nature one, because if it is positive in the sense, I mean, if it is north in the sense, this is also, if you take south, then it attracts. Then by this surety test will not be happen. If it is north, this is also north, then it gets repelled. Then that time we will understand, oh, here some field is existing. Therefore, we will not enter there. We will understand that in this region some field is existing. Same thing we studied in electrostatics also. We are bringing a charge from infinite distance to electric field, which is with respect to the source charge, right? This we studied. Did you remember that?
Yes, sir.
The same application is here. When you are bringing the charge, the same nature we are preferring. Why the same nature? We will get repulsion. By that we will understand surety. That is we call as surest test of magnetization. Okay, that is a repulsion. By the repulsion only it happens. Next, representation of magnetic field. What do you mean by representation? How you will represent the magnetic field? The same way the electric field, how we have represented, the same manner we will represent the uniform magnetic field. The word uniform is indicating equal here. All the magnetic field lines are having the same direction. That is also a unique direction. Okay, in the plane. Now, here you are seeing cross marks, which are always acting inwards. Okay, this is also uniform, but into the screen. This is all dotted. This is all perpendicular to the plane outward. Both are perpendicular, but this is inward. That is outward. We say here. This is all the pattern of uniform magnetic field lines. What are those? Pattern of uniform magnetic field lines. Now, you can see we studied in electromagnetism. Nothing but after the Biot-Savart law, we studied an application that what was the application is that is magnetic dipole or dipole moment. Okay, M equal to I into A, product of current into area of cross section of a loop we studied. Same way here also will come, but this is in normal magnetism. Current loop has a magnetic dipole and dipole moment we studied. That application only we are using here. See, the current I is passing to the loop. Then at the center, who is coming? Obviously, magnetic field producers. Because perpendicular to the loop, magnetic field lines are producers. Since this is a loop, it is with respect to the clockwise and anti-clockwise direction. I said clock rule I was said that time. Okay, with
Yes, sir.
respect to the view, if it is from my view here, if it is anti-clockwise direction, are you able to see my hand?
Yes,
this
sir.
this is for me anti-clockwise, so here I'll decide or I'll describe the pole of the magnet is north. If this is north means with my view this will become south automatically. Okay.
Yeah.
If it is
Yes.
clockwise, let us say, if it is clockwise, then with respect to my view at this coil position or loop position, this is a south pole. And if it is a south pole with respect to this is a north pole. That is what a clock rule. So since it is having the two poles, dipole. In electrostatics, dipole, positive charge and negative charge. But in magnetism, dipole comes bar magnet north and south. But in the loop, it's north and south like this it will get. That is the formula for magnetic dipole moment. Magnetic dipole moment. This is a magnetic dipole moment, which we are seeing here. Yeah. M equal to M equal to I into A we can say. What is this M equal to I into A? M for magnetic dipole moment. I is the amount of current which is flowing through the loop. A is the area of cross section. N cap is determines the direction of the magnetic field. Okay. Magnetic dipole moment is M equal to IA n cap. SI unit is ampere meter square. What is the SI unit here?
Per meter square.
Yeah. Now, this is exactly gives us for the clock rule. You can find here the clock rule with respect to clockwise direction and anti-clockwise direction. The polarity has given to the magnetic dipole. Now, current solenoid as a magnetic dipole or a bar magnet. Here, nothing but we are comparing uh, solenoid as well as bar magnet. How it is? We studied the solenoid in electromagnetism, right?
Yes, sir.
So, in the electromagnetism, whatever the solenoid we have studied, with respect to that, you can find here the solenoid view. Okay, the solenoid view is constructional view you are seeing in the diagram. This constructional view it shows us inward and outward of the current flow with respect to how magnetic field lines are produced. See, the above part, the constructional view completely it is showing that dot dot dot, and down you can see here all are showing only in the form of down into. This into is inward, dot is outward. So the current lines, the current flow is taking inward and coming from outward. Around that perpendicularly, the blue lines are showing that magnetic field lines. Okay. So each and every coil or every ring or wire you are finding as a one loop. Okay, one loop. Next, same way, bar magnet here, you are seeing the bar magnet. With respect to the bar magnet, south north direction, same as for the solenoid also. And the pattern of magnetic field lines non-uniform, same as it is entering at the south pole and leaving at the north pole. That is also be found in the solenoid. See, solenoid and bar magnet. You can feel here illusion,
Yes, sir.
right? Everything is same. Just here we are using cylindrical view dotted lines. Here you are seeing here rectangle. Only there it is, we are using the battery for producing the current. Depends on the current, there the magnetic field line changes. Obviously, we studied already in electromagnetism, or not only electromagnetism, especially in solenoid. If you see, in solenoid, we can increase the magnetic field lines. How? Our magnetic field. How? By increasing the number of turns in the coil, one thing. By increasing the area of the coil, second thing. Third thing, the amount of current which is flowing through the wire, if it is increases, also magnetic field increases. Then one more thing, the fourth one, if you are inserting any soft iron, if you are inserting any soft iron, by that we can increase the magnetic field produced by the solenoid. But coming to the bar magnet, since it is a bar magnet, it is made up of magnetic material. We cannot alter the magnetic field in this. We cannot, in solenoid, by changing the current direction, we can change the polarity, right? But in normal magnet, we cannot change the polarity, right? At the same time, here you cannot increase or decrease. Decreasing, we will not. It is not depends obviously by the usage. It will decrease, but sudden increase, sudden decrease is not possible in the case of bar magnet. Okay. Now, these are all differences between the solenoid and bar magnet. Question can be given in the exam. What are the similarities between the bar magnet and solenoid? What are the dissimilarities between the bar magnet and solenoid? Similarities, both are having the same polarity, Both are having north and south poles. Both produce the same magnetic field pattern. Both will attract. Okay. Both behaves as same in cylindrical nature or in rectangular form only. Okay. Always the magnetic field lines are entering at the south pole, leaving at the north pole. In both cases, same. Okay. Magnetic field lines are closed loop lines. This is extra property of field lines. But dissimilarities, we cannot alter magnetic field in the bar magnet, we can alter in the solenoid. We can change the polarities in solenoid but not in a bar magnet. Right? So these are the dissimilarities. Now you are seeing exactly the bar magnet. Now these are the most important things which I am going to tell you now. South pole and north pole. You are seeing the positions of P and T in a yellow points. These 2 points are the magnetic poles where the total magnetic field strength is located. Means here inside the magnet there are the domains. Domains in the sense small, each and every particle is having the magnetic property and polarity also. This all togetherly resultantly locates here and here. So this is the positions of the poles. These are the now this is magnetic moment which is acting, and the length between the two poles is called as magnetic length. Remember, note this point. The length between the length of outside magnet or the size of the magnet is called as geographic length. Okay, geographic length of the magnet. This is magnetic length. Remember always. If you wanted to relate these two, there is a ratio. I'll come back to that. Magnetic axis. Here, one more important thing. If I'll draw a line like this, if I'll draw a line like this, the line, if it is along the axis, if I'll draw, that we call it as like this. The center, if I'll draw an axis that we call as magnetic axis. This is an imaginary axis beta graph. This is just imaginary axis. We assume it. Otherwise, physically there is no axis like that. Next, the distance between the poles of the magnet is called as magnetic length of that particular magnet. Next, the distance between the ends of the magnet is called geometrical length. Now, around if you take the difference between them, the ratio of the magnetic length and geometric length is nearly this 5 by 6. The ratio of magnetic length and geometric length is equal to 5 by 6 is approximately 0.84 we can write in the number. Next, magnetic dipole and dipole moment. These are the important definitions we need to understand also. Dipole and dipole moment. We have seen magnetic dipole in electromagnets. Now, in normal magnets, what is a magnetic dipole? Usually, bar magnet itself is having the two poles, right? So we can say it
Yes.
is a magnetic dipole. They have equal and opposite strengths separated by a small distance. So that we call as magnetic dipole. If the distance, if you are taking 2L and the poles, whatever the poles are there, it is having some amount of strength that we call it as pole strength. Okay, because it exerts force on another magnetic substances or another magnets. So therefore, the pole strength, product of pole strength and its separated length, we call it as magnitude of magnetic dipole moment. Dipole moment is different. Magnetic dipole is different. Dipole moment is different. Okay, same charge. Two charges are there. Electric dipole is different. Dipole moment is different. Dipole moment possesses the vector nature here. That is, we will write capital M is a magnetic dipole moment in the sense that equal to magnetic pole strength. Small m is pole strength. Some books it will be Small m only taken as momentum sometimes. Okay, but be aware of that. Here we took here capital M equal to m into 2L into L. What is this L? It is indicating the, it is not L, sorry. M into 2L into I, where I is indicating the vector nature, unit vector, direction of the dipole moment. Okay, so pole strength, always we will write ampere meter, we are writing as a units. The direction of dipole moment is from south pole to north pole always. Same like in electrostatics, we have electric dipole. Electric field direction positive to negative, but always electric dipole field direction is opposite to the electric field. Same here, magnetic dipole, direction of the dipole moment is south pole to north pole. Okay, but magnetic field lines outside it will move north pole to south pole. But this is along the axis we are taking, so south pole to north pole it is. Magnetic dipole moment is product of magnetic pole strength and its separator length by 2L. Okay, this is
Yes.
very clear definition magnetic dipole moment. Of course, coming to electromagnet, coming to normal magnetism, it gives same dimensions in units. Okay, so both cases magnetic dipole moment gives the same meaning, but approach is different since it is here normal magnet with respect to that. There it is electromagnet with respect to current. We have to approach. Still, you can look at here the units they have written ampere meters only. Okay, it is units as taken from the electromagnet only. Okay, so this is
Yes.
about the bar magnet and magnetic axis, magnetic pole strength, and next the ratio of the geographic length and magnetic length, and magnetic dipole and dipole moment. Okay, next Coulomb's law in magnetism we will discuss in the next class. It is actually out of syllabus we don't have, but still we will have a glance on this because it helps to understand the other concepts most of the times.